street light is 6 meters tall. This is kind of one of the classic calculus problems. If you could, I suspect if you were talking to someone from Germany or China and who had taken calculus and you mentioned the walking away from a street light problem, they would probably know what you meant. And it goes like this. We've got a stationary streetlight. Theirs is 6 meters tall here. And then somewhere over here we have a person, 2 meters tall. And if you draw a line from a light source that goes just barely over the top of your head, where that strikes the ground or the wall or whatever surface you're talking about, that's where the tip of your shadow is going to be. Your shadow is going to start underneath your feet and extend outward to wherever this line is. And because this line went over the top of your head, over here will be the top of your shadow's head. If you're standing in very close to the light source, almost right underneath it, then this line comes down very sharply and you end up with a stubby little shadow that's mostly under your feet. And as you get further and further away, your shadow stretches out more and more and covers more and more distance. You're moving, and your shadow always starts at underneath your feet, but the tip of it also moves and stretches out, gets more elongated as you get further away from the light. So we have to combine those two effects to figure out the answer to this one, which is how fast is the tip of your shadow moving as you walk. So there are a few ways to set up the triangle in this problem, and I'm going to do the first one that I thought of, which does a decent job of it, and then I'm going to do the one in the workbook because it's different and interesting, and we're going to get the same answer either way. So with a lot of these problems, there are multiple setups, and that's fine. So things we're all going to agree on is that the light is 6 meters tall, our person here is 2 meters tall, and what I used for variables down here is an x, which is the distance from the light to the bottom of the person's feet, and then from there I put in an additional distance s for shadow, which is the length of the person's shadow. And we can set up an equation using these things based on similar triangles. We've got one triangle, one moment while I switch colors. We have a small triangle out here that's from the tip of the shadow just to the person, and then we have the big shadow out here, which is from the tip of the shadow all the way back to the street light. All the dimensions are bigger in that one, but the ratios are the same. That's what similar triangles means. And the setup I came up with is I said S is to 2 in the small triangle. So that's the bottom to the vertical side. S to 2 is the same as, now down here you get x plus s to 6. Okay, so base of the small triangle, height of the small triangle, base of the big triangle, height of the big triangle. Now, we can multiply that out and get it to clean up a little bit. If I cross multiply this, if I go s times 6 and 2 times s plus x, I get 6s equals 2s plus 2x. Subtract 2s from each side, and we get 4s equals 2x. And while we're at it, we can divide both sides by 2, so why not? 2s equals x. Okay, so this is telling us something which I didn't see coming, that the shadow height is always half the size of your distance from the streetlight. Not critical to solving the problem, but it's kind of interesting. The main thing we want to do with this is they've given us how fast the person's walking away from the streetlight, how fast x is changing. That value right there is dx dt. It's how fast is x changing as time changes, and the answer to that is 1.5 meters per second. Positive because x is getting bigger. So if we differentiate this, well, first we get 2ds equals dx, divide both sides by dt, and now we have a rate equation. And it says the ds dt, how fast the shadow's stretching out, times 2 equals dx dt. So, okay, we can plug in for that. 2 ds dt equals 1.5. Divide both sides by 2. ds dt is 0.75 meters per second. Okay, now what this setup has that's kind of unique, that I don't think we've seen before, is that you end up using two rates at the same time. What's happening here is this person's feet are moving away from the light at 1.5 meters per second. Their shadow is also stretching at a rate of 0.75 meters per second. It's getting longer as they get further away from the light. Your shadow elongates. And so to find the movement of the tip here, you actually need to do dx dt plus ds dt, because both of those things contribute to movement of the top of the shadow. You have to do 1.5 plus 0.75, and from that you get 2.25 meters per second. That is legitimate. It's a little bit unusual, but it's fine. It's just a matter of combining those two effects. We said the distance to the tip of the shadow is x plus s, so not surprisingly, the rate of change of that measurement is dx dt plus ds dt, both of those rates together. So doing that, 2.25 meters per second. Now, having said that, that's a correct result, and now I'm going to wipe it out, and I'm going to go through again the way the workbook does it, because they do an interesting setup that also works. And theirs goes like this. They still use similar triangles, but they use different similar triangles. So let's clear out this labeling here. And they construct a triangle that I wasn't expecting to use. They agree with me about the orange one. No, I'm sorry, they don't. I have to clear that one out also. My bad. Okay, they set up two triangles, and here's how theirs go. First, they make a triangle from the lamppost out to the top of the person's head. This blue one here. They have that triangle, and then they have the great big triangle, the same one that I used. I could have left that in. So they have the small blue and then the big red. This is not a real natural way to construct the triangles, in my humble opinion, but it does lead to some nice math, and I'm sure they realized that when they set it up, so fair enough. For measurements, they have an X, exactly like I did, from the base of the light to the person. And then they have another value that they call Y, which is from the lamp to the tip of the shadow. So this Y, or dy dt, is the value we're trying to find in this problem. Their big triangle is still 6 meters high because that's the height of the lamppost, and then they need this height for the small blue triangle, which isn't given, but we can find it easy enough. If this overall height is 6 and the person's 2 meters high, there must be 4 more meters in here. So you have to come up with that one additional value of 4. And doing that, we now do special triangles. And we can say for the small triangle, x is to 4 as y is to 6. Okay. Base of the small triangle, this distance is x, so is this. Height of the small triangle, base of the big triangle, height of the big triangle. Multiply across, and you get 6x equals 4y. Divide by 2 if you like. Differentiate. I'm going a bit fast because this is getting a bit long and I don't want to exhaust you. Divide by dt. And we get 3 dx dt equals 2 dy dt. dy dt is the distance from the lamp to the tip of the shadow. That's the one we're trying to find. So if we divide both sides by 2, we get dy dt is 3 over 2 dx dt. And dx dt, we know, is 1.5 meters per second. That's 1.5 times 1.5, which comes out to, lo and behold, 2.25 meters per second. So same result with a different construction. Use whichever one you like better.